All right. Hello, everyone. Wow, we're so full. I wonder if people thought we had a lab today. There's no lab today. There's no way we're doing it. We haven't covered anything. But I'm glad y'all are here. You're welcome to leave if you want to. I'm still going to teach. Yeah, there's no lab today. We only have one more lab. It's on the calendar. I'm pretty sure.
I have my own
I think I updated. Maybe I didn't. I don't know. There's one more lab. It's next Thursday. Next Thursday is the lab.
So the last week of school.
Kind of, sort of. Yeah. Speaking of which, there is only 4 class days left if you don't include the final. I'm not counting the final as a class day. Y'all got today. You got Tuesday, then Thursday, and then the last Tuesday. So we're gonna hope we should be able to. We are gonna get through electromagnetic waves in the next 3 days. Pacing wise, I think we're just how my lecture class went should go smooth. So that means the last Tuesday is a review day. Now, something of note is I've already basically made all the review that I'm gonna make. So if you're like, what do you mean? I'm not gonna make a big old final review because most of the tests. What's the first kind of big chunk? Test 1. There's already a test 1 review. Feel free to look it over. Test 2, that's also a big chunk. That already exists. So I will make a 5 or 6 PowerPoint slide for this electromagnetic waves, but otherwise, everything else already exists. All the study resources you all kind of need for 80 to 90% of the test already exist. So I'll make a shortened version of this, like a summary and a couple problems for this for the review day, but otherwise we'll basically just be reminding ourselves of the things from test 1. I might make up some problems kind of on the fly or something like that. We will do review, and the review will largely be emphasizing the stuff from test 1. Like we will dabble in test 2. The reason we're not going to really spend a bunch of time on we're going to spend a bunch of time on test 1 is because that was a long time ago, relatively. It's the stuff you're most likely to have forgotten.
Is the final multiple choice only?
The final will be multiple choice only. Currently, the plan is about 40 multiple choice questions, which is a lot of questions. There is no free response because there's not time to grade free response effectively. It's really tight. Now, that does mean that So, the multiple choice will include problems of more complexity than your prior multiple choice tests. Why? Because there's no free response. So I'm going to take the free response and cycle it into the multiple choice. Now, that does not mean I'm going to put multiple choice questions that take you 10 minutes. But they'll be pieces of it. It wouldn't be unreasonable to say build the integral of this, but don't actually solve it. Or, we'll figure. I'll try to think of better examples of that. But basically take pieces of the free response that you all been doing, and that's the expectation. For example, this last test, I can finally talk about it because I had my last makeups today. One of them had you combining a bunch of resistors together. That would not be an unreasonable thing to ask as a multiple choice question. Hey, here's a circuit with a bunch of resistors. What's the net resistance? Yeah, sure, it takes a little bit, but it's not super, super long. It's not 10 minutes long. So yeah, just be prepared that the multiple choice won't be as you do need to still be able to do the level of the free responses. They're just going to be intermingled. All right.
All right. This one's an original from my partner. So, what do you call a famous space heater? A star. Think about that one.
Yeah, it's good. Test performance. The test performance was super high, to the highness that when I've told a couple other people, they're that's too high. But I don't say it's a bad At the end of the day, the test was fair. I feel and I'm very pleased with how you all did on it. Yeah, again, you can see the distribution there. The first response is in progress. That will be done by next Thursday. Should be. But those were also looking pretty good based on the ones I started grading some of them, and those are looking fairly equivalent to the multiple choice. So all that's good. But yeah, I think that's basically it. Is any questions, comments, concerns? I'll chat more about the free response on Tuesday after I've graded more of them. I'm going to be starting to make your all's final, so I'll be able to give you all kind of like reminders and things like that throughout the coming weeks. But yeah, I'm optimistic. All right, so waves. I think I previously told you all we can't cover AC circuits because we had 3 days to cover things. I chatted with some people and electromagnetic waves, and I say people, other professors. We kind of landed on electromagnetic waves. Why? Well, waves are more physicsy than AC circuits. Circuits are more engineering than physics. They're very more practical. Physics is more of understanding reality, and so waves kind of are a bit more physicsy. If you need AC circuits, you'll see it in future classes. You can use the PowerPoints I use to help learn it, yada yada. Waves are super, super important for you to know if you want to understand anything about wireless communication. So in an engineering sense, if you want to understand anything about wireless communication, you need to understand waves. Physics majors, you all need to understand waves because quantum mechanics, among other things. Everything in the world can be broken down into waves. There's something called a Fourier transform, which basically takes any function and turns it into an infinite sum of sine, which are wave equations effectively. So this is going to be a little mathy, and so the derivations will be a little mathy, but the results of this stuff is very, very far-reaching. And there's going to be some cool simulations I'm going to show you all that you can play around with on your own that show how light works. And they're super cool. I'm really impressed with what this person developed. You'll see it when you see it. But yeah, my goal, the equations here, let's actually just jump over. I have at this point made all the things. Problem set 3 is just electromagnetic waves because that's what's left over. So that's all done. It's about 21, 22 questions, something like that. Usually, there's several types of questions in there, yada, yada. Make sure you do them. So this last 2 rows are the last 2 things I'm going to be covering. Remember, the formula sheet is a fantastic summary of everything I've taught you. So these are the things that we're going to kind of be going over. We're going to mainly focus on these first 2 to begin with. The ordering of these isn't quite perfect, but it's pretty close. So yeah, this is it. Now, most of these are fairly simple. Like this intensity one's fairly simple. These ones over here look fairly simple. This one right here is the wave function. That's my goal. By the end of this class, we're definitely going to cover this in a little bit more. But my goal is to help you understand where this comes from. Because just looking at it, it's got a lot of variables in it. Probably more than any equation on this formula. I don't know if it's got more. It's the longest, I think. Whatever, it's got a bunch of things in it. We're going to build this equation together. That's going to be one of our goals today, and understand where it comes from. And I'm not just going to pull it out of thin air. That's always an emphasis in any physics class. Everything we teach you is from ground principles on up. So, yeah, waves. We're going to talk about light's a wave, what waves are, wavelength, frequency, electromagnetic spectrum, how light bends. There's going to be a lot of really cool stuff in here, in my opinion. Again, a little mathy in some areas, but the consequences of all this stuff is going to be hopefully cool. You need to understand electric fields and magnetic fields. That is critical. Why? Because they're electromagnetic waves. It's literally an electric field and a magnetic field that make a wave. So if you don't understand either of those, you're going to not understand half of it. This is why we can't do this earlier in the semester. This is why this is something we have to cover at the very end. It's because electromagnetic waves are made of electric fields. We spent the first half of the class on electric fields. We spent the second half of the class on magnetic fields. Now we get to combine them together. And this is probably one of the best arguments for that fields are a real thing, is the fact that light is just a field that travels through space. It's not a physical object. You can't touch light. It doesn't have any mass. It's just this electric field and magnetic field that oscillate through space. So is light real? I guess the real fields are, whatever you want to take that to mean. All right, so, great. First thing, just to sell it, light's an electromagnetic wave. There's a picture of it. We're going to see this 30 slides from now. We're going to see it again. Every single wireless signal you all can think of is an electromagnetic wave. Every wireless signal. Radio waves, those are electromagnetic waves. A flashlight, obviously, in some ways, that's, when I say it's a signal, you can shine a flashlight at someone and you do Morse code or whatever. Your TV remote, Wi-Fi, Bluetooth, every single cell phone signal, literally anything where you push a button and there's no wire connecting it to something else, and then something magically happens, there's an electromagnetic wave. You all right now exist in a soup of electromagnetic waves. Why do I use the word soup? It's because they're all mixed together and they're all happening through every single radio broadcast. Any signal your phone can pick up, why can it pick it up? It's because it already kind of exists there, kind of, sort of. So like when you all call someone, every single phone call that's happening in this building or anywhere nearby, that wave is everywhere. Every single radio signal that's out there, it's all passing through your body right now. And it's a juxtaposition of all of them together. It's kind of a crazy idea. You can't see any of it. All the Wi-Fi signals, all the Bluetooth signals, all of them are right now everywhere in space happening at the same time. And your device, using a bunch of clever engineering, can isolate the one it wants. Engineering and coding. And it's a crazy idea. It's something obviously none of us can see, but it's always happening. And it's foundational to our society. Most people don't understand.
Is there anything preventing someone from listening to a call that they not?
Yeah, is there anything? So they're encrypted. So the data comes in, and even if you could pick up the signal, you'd have to make meaning of the signal. So it's almost like you could watch someone turning a flashlight on and off in the distance, and you could intercept that signal. Will you know what the flashlight dots and dashes mean? Not unless you have the right code to interpret it. Yeah, so that's a good question. Yeah, you can pick up any signal you want, whether or not you can interpret what all the data means, or whether or not you'll know what signal to pick up in the first place. Because again, it's a soup. How do you pull the one that is significant? Yeah, so we need to understand waves. Now, as a refresher, a wave is just something that periodic motion and waves are two sides of the same coin. Periodic motion is something that repeats itself. You know, a wheel spinning in a circle, a spring oscillating back and forth, an ocean wave track. All of these are the same thing mathematically. You can represent them all as a wave. A wave is just something that periodically oscillates, so we need to understand periodic motion. Again, incredibly important thing for every single one of you, regardless of your major, is understanding periodic motion. Because there is something called a Fourier transform that can convert anything to an infinite sum of periodic motion, and it's super useful. All right, angular velocity. Again, so this slide is not anything actually new. There was a typo, I fixed it, so if you're looking at yours and it looks slightly different, there's some typos I just updated. But yeah, angular velocity, rate of change of the angle per second, regular frequency. That's the rate of change of how many cycles per second. We're going to be seeing both. Unfortunately, they have the same units. Both have units of hertz. So the units for angular velocity is hertz. So this equals hertz, H-E-R-T-Z, hertz. The units for frequency are also hertz, but they are not the same thing, and it's very unfortunate. The reason is radians and cycles aren't real units. They're quasi-units. So like when you write the actual units, so I will tell you on a problem what type it is. I'll say angular velocity, or I'll just say angular frequency, or I'll say regular frequency. I have to explicitly kind of say the word, or tell you radians per second or cycles per second. If I just told you something had 60 hertz, it's not clear what that is. It's one of the really unfortunate ambiguities that emerges, and I don't really know why it still exists. Whatever, it is what it is. All right, new one at the bottom, new/not new, period. It's the time for a full cycle. How much time does it take for one full wave to pass you by? That's the period. It's 1 over the frequency. That's really easy to prove if we just look at the units. The units for frequency is how many cycles per second. How many full cycles occur per second. What is period? Period is how many seconds it takes for one full cycle. If you just look at the two, they're just inverses of each other. So that's the, well, period is 1 over f. All right, so math. All right, what is a wave? Again, a lot of what I'm going to be teaching you on this first 15 PowerPoint slides, stuff you might have learned in middle school and high school, but I need to make sure we all have a good foundation going into this stuff. So what is a wave? It's a disturbance that propagates or moves from the place it's created. What is being disturbed depends on the wave. If it's a water wave, it means the water is kind of oscillating up and down. If it's a string wave, you got a string and you wiggle it, it's the string. If it's an electromagnetic wave, it's an electric field that oscillates. Something that wiggles. When we use the word disturbance, it's something that's wiggling up and down. In the case of sound, it's in and out, so that's different. But yeah, they have all sorts of interesting properties that you all both know, but you might not realize the full consequences of them. So waves spread in all directions. You all know this. You drop a rock in a pond. It makes a wave. What does that wave do? It spreads outwardly in all directions. You get those ripples. Those are waves. And as they go outward and outward, they get smaller and smaller. We're going to learn about why that's significant. They bend around corners. This is also something you all know, whether or not you realize it. If your door is slightly cracked and the hallway light is on, your entire room gets slightly lit up. It doesn't act like a laser and goes through it only in a very finite path. The whole room gets slightly brighter. Why? Because the light bends around the corners. It constructively and destructively interferes with each other. Let's see. What's a good example of this one? So I'm gonna have a nice slide later that kind of shows some pictures of it. I can't think of any specific examples that you might have experienced with that one, but it is something you know. Maybe if you're in a pool, when all the waves kind of run into each other, you get bigger points and lower points. All right. What I want to point out is a simulation. I'm going to be using this a bunch in this class. There's a lot of cool stuff that exists online. This guy / website, this guy who made the website, he has a ton of really cool simulations for varieties of things. So we're going to be using this one a lot because this one is you can do so much with it. It's just waves. It's waves, and I'm going to go through and kind of show you all a few things. So this is what we call like a point source. Imagining someone's like bobbing something in the water, kind of up and down, and this is what it looks like. The bright spots are the high points. The dark spots are the low spots. What's cool is there's like a 3D view of it, so you can kind of see that a little differently. You can kind of see that they get weaker as time goes on. You can make the simulation go faster. You can make it go slower. So if faster, it's faster. Slower, it's slower. You can change the frequency. So i.e. how quickly it's going to oscillate. The quicker it oscillates, you get higher frequency waves that go from it. So there's a lot of cool things you can do this, but one of the things I want to show, there's a few examples he has here. This is a single source. So just to kind of prove some of the things I've shown you. These are waves, oscillating. You're great. One is that they bend around corners. So this is going to be really funky to see here. So this is a wall. The light cannot go through the wall. You're going to see it's going to hit the wall. Can't go through it, but it can go around it. And when it goes around it, something that's kind of a crazy idea with waves is that everywhere on this wave, you could think of it looking like this. That's not going to be the best description. Everywhere on this wave acts like a point source, i.e. generates this. So when it hits this corner, these corners are basically going to act like point sources. You'll see what I mean. And they then make these radially outward. They make their own little radially outward, and this is the whole light bending around corners. This is why light does that. Waves, they spread in all directions. That's really all you need to know to understand that. You get these patterns of constructive and destructive interference because we now have effectively 2 point sources instead of just the one. You get these places where it's brighter and where it's darker. We call this a fringe pattern. This is how light was originally discovered to be a wave, was these fringe patterns. And if we look at the 3D view, you can maybe see it a little bit better from the side. You get these places where there's not really any wiggling happening at all. That's that destructive interference. They're canceling out. And you get it where it's happening a lot. And that's that constructive interference. So great. There's that. There's also the two-slit experiment, which we're not going to get into too much in this class, but this is a notorious one in physics that also proves light's a wave. So just to help us understand what's going on here, we have something called a plane wave. What is a plane wave? It's, like an ocean wave is a big, long wave that looks like almost like a wall that's kind of traveling towards you. That's a plane wave. It's this big, you can almost think of it like a flat plane heading towards you. So here, this generates some plane waves. There they are, big, flat waves. And when they hit this, you get 2 point sources. And again, we get that interference pattern. And that's useful for a variety of things, but it also shows the characteristics of light. And yeah, all sorts of crazy things in here. We're going to kind of refer to various ones. You get the sonic boom. You're like, what is a sonic boom? This is why sonic booms happen. As the thing moves, you get this wall of constructive interference, and that's the shock wave that happens from it. Waves are cool, but if you don't understand what waves are, you can't understand why any of this happens. And yeah, again, just so many things. And we're going to refer to some of these throughout it. But it's a cool thing to open up, play with yourself. It exists. All right. So, great. Okay, characteristics of waves. Again, this is something you've probably learned in middle school, high school, but I just want to make sure we all know the terminology. Every wave has an amplitude, frequency, and wavelength. This is just things you can measure on a wave. And these are words you've probably seen before. Wavelength is the distance between two identical points in a wave. Not only means the value at that point, but also the slope. That is variable units of m, lambda. So we're going to do a problem on that. Again, you've probably done this before. Frequency is how many times a wave oscillates per second. How many times a full cycle occurs every second. And amplitude is the maximum distance from equilibrium. These aren't hopefully surprising things. But if they're new to you, no problem. There they are. These are things we need to be acquainted with, though. And let's see if you do know them. And I had to update this because the old graph was had a weird oddity to it. So this is the new one. So if you're like, this doesn't look like the one I downloaded, this is one of those typos that I changed. So hey, here's a wave. What's the wavelength? Is it 2 meters, 3 meters, 6 meters, 10 meters? There's only one right answer. Fairly straightforward. Give you all like a minute 20 on this. The old graph was bad.
Yeah.
Because all the blocks counted by 1.
Yeah.
Except the first one was counted by 2. I'm like, who made this stupid graph?
I didn't notice.
No, I didn't notice it either.
I just noticed that the answer was
Yeah. No, I didn't notice that. The other thing was like, hey, if I did here from here, it gives me 5, and if you here to here, it's 6. Like,
I should not be happening.
who does it? Who makes the graph for the? I don't know. I mean, I'm still in front of people.
Yeah. We all
All right, give you 20 more seconds. Again, probably just making sure we're all on the same page. All right, 5, 4, 3, 2, 1. Great. Wavelength, distance between two identical points. Now, it's fairly tempting to pick this one, and that's perfectly fine. That's wavelength. You could also pick this one and this one. That's also the wavelength. You could also pick this one and this one. That's also the wavelength. You could pick this one and this one. That's also the wavelength. Notice all the arrows are the same size. It doesn't matter what you pick. The distance is always the same between two identical points. And the reason we use wavelength is wavelength makes you think it's the length of the wave, which in some ways it is. But say I had a wave like this, the answer here is not going to be how big this wave is from start to finish. Because, what if I shine a light into space? What's my wavelength then if I measure from the beginning to the end? It goes forever. You can't measure the beginning to the end. So what do we measure? From one point to the next, we measure what one full wave looks like, and then it just repeats itself. If you understand one piece of it, you understand the entire thing, is effectively the idea. So great. In this case, it is 2 meters. Fairly straightforward. Everyone got it pretty much. Yay. Here's a pretty picture with all the things. You've probably seen this before. Vocab, right? Okay. Now, these waves move. So that's something that's going to kind of introduce some complexity here. These are not stationary waves. So for example, this wave in this picture, we're going to learn moves. It can move right, it can move left. So that means at some later time it's going to shift. We need to understand, we call that velocity of the wave. The wave physically moves. Let's derive it using just units. Using just the units for wavelength and frequency, determine the expression for velocity. So you need to ask yourself, what are the units for wavelength? What are the units for frequency? What are the units for velocity? Then do math to make them equal each other. How can I combine wavelength and frequency together to get me the units for velocity? Is it v equals f lambda, v equals f over lambda, v equals lambda over f, or v equals 1 over f lambda? This is a hand-wavy way of deriving it. This one I'll go around and ask you all questions. Make sure your brains working. All right. Okay. Okay. Frequency is 1/seconds. Okay, and then what's used for wavelength then? Distance. Yeah, frequency is 1/second, so multiply it. Yay! All right, 10 more seconds. I think y'all are pretty much there. Yeah, looking good. All right, in 5, 4, 3, 2, 2. All right, I'll just leave it open for a second. All right, the units for wavelength are meter. The units for frequency are hertz, specifically 1/seconds. The units for velocity are meters per second. So, how do I combine meters and 1/seconds to turn into meters per second? You multiply them. Meters times 1/seconds equals meters over seconds. So, lambda times F equals velocity. Yay, we derived it. Another way to kind of understand that this is velocity is, I'm going to use a kind of a jank example, but it's fine. Say I have semi-trucks, and I see a frequency. Now, these are back to back to back because they're like wavelengths. Remember, they got to be smashed together. So you got a truck, then a truck, then a truck, no space between them. If I have a frequency of 5 hertz, that means every second I see 5 semi-trucks. That's what the frequency means. Every second, 5 semi-trucks passes me by. So great, that's 5 hertz. Now, let's say we had cars, and it was also a frequency of 5 seconds. Again, they're one after the other. So these are smaller because they're cars. I still have a frequency of 5 hertz. What I hope you can kind of see with this maybe funky analogy, if my semi-trucks had a frequency of 5 hertz and my cars have a frequency of 5 hertz, my semi-trucks need to be going faster to be able to see 5 every second. Why? Because there's more. Look, they're longer. They have to travel faster to travel more distance in the same time. That's kind of the idea here. Both are happening every second. So that's kind of where this velocity comes from. If you have a bigger frequency, a bigger wavelength, but the same frequency, velocity is going to be bigger. By that example. So, great. There it is in the next slide. It's how fast a wave travels. These waves travel. They move. So just to show you kind of what I mean by they move, because we're going to be seeing this a bunch. Great. There's my wave. Here's what's going to happen. Here's the one of the challenges with this whole wave thing. Here's the reason I'm going to be using simulations. The wave I just drew is the wave at some time. At some later time, it's going to move. So this wave, so I can't actually draw the wave. I can only draw the wave at one time. If I want to draw it another time, new graph. If I want to draw it another time, new graph. So this is a funky graph. All the graphs you all been doing up to this point were a static graph. You all now have to kind of get in the mindset that this wave, this wiggly line is going to be traveling to the right. Literally shifting along the axis. That's just just foreshadowing in the future, this is not only going to be a function of where you're located, it's going to be a function of how much time has passed because the graph is going to physically change every second. That wave is physically going to be moving to the right every second. So this is one of the first times where we have a function not of just one variable, but two. And that introduces some funkiness. So one of the things I mentioned here, if v is a constant, then f and lambda are inversely proportional. Meaning as one goes up, the other goes down. Why is that? Let's just make some examples. Let's just say the velocity is 10 for two cases. One case has a f of 2. The other one has an f of 4. You can just do the math. This is going to be 5. This is going to be 2.5. As one goes up, the other goes down. So if frequency goes up, wavelength must go down. As wavelength goes up, frequency must go down. They're if they equal the same number. And we're going to learn that all light travels at the same speed. So that's why that's relevant for us. So great. Let's see if that makes sense. See if y'all can put this together. Two waves are traveling at the same velocity. One has a wavelength of 300 nanometers, which is a little bit lower than green light, I believe. Need to fact check myself on what wavelength of light that is. Wave 2 has a wavelength of 150 nanometers. I think that's like ultraviolet. How do their frequencies compare? Don't worry what color light they are, but just fun fact. Light is roughly in this ballpark.
Green light's about 500.
Green's 500?
Yeah.
Okay. And I think smaller wavelength is purpley. Yeah. So purple's 300 is roughly purple. 150 is roughly ultraviolet. Not that it really matters for this problem. Figure out how the frequencies compare. Have fun. Be careful on this. It's really easy to mix up the answer. It's already happening. Give me your rationale. Okay. So shorter wavelength, bigger frequency. One goes down, the other one goes up. So we kind of check out these answers. Which these are small wavelength? Which one shows bigger frequency? Smaller wavelength, bigger frequency. One goes down, the other one goes up. Smaller wavelength, bigger frequency. Bigger wavelength. So this one is your frequency.
Still great at this point.
Yeah.
How's that going?
Probably do the staff.
That's good.
And so we can just check our logic here.
I meant like
One of the ways.
I was saying
F1
it in
and double
order.
Y,
Yeah. Sorry.
That's why I've been double.
Yeah.
This
I just like said it the way I write it.
yes. This makes sense.
Yes.
Sometimes it'll be like the most simple. I'm just screwed my next picture.
It is. Think of a number for F2. Any number you want. What's one happen?
At least my she drops the lowest one, and my average between the first two is 9.
Because it's one.
One of the things you all need to be careful of, again, this is a classic mistake that happens, so I want to make sure you all are thinking about this. If I answer A, what's bigger, F1 or F2? If I picked answer A, which one's bigger? Make up numbers. If I made F2 10, what's 2 times 10? So answer A says that F1 has twice the frequency of F2. This is something that people get mixed up all the time. They see this, they want to rearrange it. So, to reiterate answer A says the frequency of 1 is twice that of frequency 2. The answer B says frequency 1 is half of frequency 2. It's smaller. Third says they're the same. Fourth says they're not enough information. So, make sure whatever you come up with matches that logic. Your answer should make sense. All right, in 5, 4, 3, 2, 1. All right, we're going to do this conceptually, and then we're going to do it mathematically. Which of these has a bigger wavelength? 1 or 2? 1. 1 has a bigger wavelength. What did we just say in the last slide? If the velocities are the same, as one goes up, the other must go down. So if one has a bigger wavelength, it must have a smaller frequency. The frequency of the first one must be smaller. Why? Because it's got a bigger wavelength. There's only one answer up here that says a smaller wavelength. This is the only one that says it has a smaller wavelength. Now, there's a couple ways to prove this. I'm going to do it the way I traditionally do these problems, and then I'm also going to show you another way. 3 ways. So you have V equals F times lambda. We care about frequency, so let's isolate that. Great. There's frequency, and let's call this 1, 1, 1. We also know that lambda 1 equals 2 times lambda 2. It's a nice little relationship for us. So we can also then write this one down here, frequency 2 equals V2 over lambda 2. We can rearrange this equation to do lambda 2 equals lambda 1 over 2. You can then plug that in. And you get that frequency 2 equals 2 times frequency 1. And you might look at this and be like, but that's not what the answer says. This is where you got to be careful. Frequency 2 is twice of frequency 1, so that means frequency 1 is 1/2 of frequency 2. Make sure you have it in the right order. That's one way. Then one of your other peers actually did it in a way that might be a little bit more straightforward. If V1 equals V2, you just set them equal to each other. So you could do F times lambda 1 equals F times lambda 2, and then you can literally put in the numbers. F1 times 300 equals F2 times 150. And you get the result that we want. So many ways to do this. Something you all should definitely be able to do, though. If this is different, how is this different? All that jazz. Looks pretty good. But yeah, the major idea here is as one goes up, the other goes down, assuming they're the same velocity. That is an important assumption. All right. This problem, I just need to give you one piece of information to solve. There's a bunch of steps, but it's a very easy problem. How long does it take for a radio signal to reach you from a radio station, which is 161 kilometers away? Fun fact, that's almost exactly 100 miles. I only know that because I looked it up this morning. Which is, I guess, supposedly roughly where Tampa, kind of, sort of, ish. I don't know. Somewhere in that vicinity. It's a good distance away. It's not very close. So how long does it take to reach you? If the station operates at 1 megahertz, how many wave crests does it send out every second, this radio station? And how far does it travel in 1 second? And what's the wavelength for this wave? There's only one piece of information I need to teach you. It's something you've also probably learned in middle school and high school. And it's something we're going to learn. We're actually going to derive this in this class. It's that this radio signal is light. And that light travels at the speed of 3 times 10 to the 8 meters per second. I haven't taught you that. We're going to derive that next class, actually. We're not going to get it from experiments. We're going to get it from equations, which will be kind of cool. From values derived from experiments, but whatever. So that's the only piece of information you'll need extra to solve this. So there it is. Try it out. You got this. put the answers in a little bit. Some of them give too much away.
Is mega 10 to the 6?
Yeah, it's a million. Yeah, that one I had to check myself several times. Yeah. I'm pretty sure this is true. So FM radio stations, 98.6 red. That is literally, I think, the megahertz.
Oh, really?
I'm pretty sure of that.
It's true for either FM or AM. I don't know which is the
Yeah,
one. I
that's
always mix it up. I think it's AM, but it could be also not.
Yeah, no, it's FM. It might be AM as well. AM's different numbers.
Yeah.
Oh, those are,
Yeah, megahertz.
those ones are kilohertz.
Okay.
So it's just lower magnitude.
Yeah, different channels. So one's kilohertz, 1 megahertz. AM for FM is
Higher
frequency
frequency.
radio anyway. And now I did like back when I was in high school, we actually used radio. iPods were just coming out.
I use the radio a lot.
Yeah, it's free.
That's all I had, really. That and CDs.
I use my CDs when I don't think about what I want to listen to. Just have one in there and it plays what it wants
I
to.
burned so many,
This?
yeah.
Oh man, so
I-
you did exist in the similar
Yeah.
Yeah.
space that I did.
I did get like an iPod in like middle school.
I got my sister's hand-me-down.
Yeah. I'm so glad that I learned how to burn CDs. I had a little boombox and all.
How old are you, Tyler?
24.
Okay. I would have expected I'm 32. So I would have expected to be more of a difference between the.
You're like almost the same as my sister, like.
Yeah, so I grew up in the age of
I think I was 7 or 8 when the iPhone first came out. I didn't get one for a long time.
Yeah,
It was 4 or 3. Not 4 yet.
until
I had a BlackBerry.
Yeah.
My first phone.
Alright, yeah, I had one at Pocket Down 911 at some point. Alright. Answer A is really simple. If y'all, and this is not as an insult, but answer A is a Physics 1 problem. And it says it's about as simple as a physics problem can get. And again, I don't say it's an insult. I say this that this is something we should definitely be able to do. And if not, practice. But how long does it take? What are we solving for? Time. You should always start with what you're solving for. You know, I didn't write that here. Great, we're solving for time. Okay, how am I going to solve for time? I know how fast I'm going. I know how far away it is. Delta x equals vt. It's just one of those bread and butter equations in physics. So t is going to equal delta x, which is going to be the 161e3. Don't forget to convert your units, 3e8. And so that means it will take less than a millisecond to reach you. They send out a signal, less than a millisecond later, half a millisecond later it reaches you. Pretty quick. Should be. It's literally the fastest thing in the universe, so can't get there any faster than that. Nothing can. All right, the next one's going to be also super easy. A lot of this is really just checking basics. Now, this next one is quote-unquote new. It's new. It's not using a Physics 1 thing. If the station operates at 1 megahertz, how many wave crests? So what we're asking is how many waves do you see? And so, okay, what does 1 megahertz represent? That is the frequency. The frequency in megahertz is times 10 to the 6. Well, that's the answer. How many wave crests do I see? It's the definition of frequency. What is frequency? Is how many occur every second. How many pass by you every second? That's the answer. So you see 1 e to the 6 waves every second. That is the definition of the unit of frequency, of hertz. It's a lot. Fun fact for you all. We were just having this conversation. I don't know if people listen to radio anymore. You may or may not. AM, FM radio, there's 2 different ones you can pick from. Fun fact for you all, if you tune into 98.7, what you have tuned in is to a frequency that is 98.7 megahertz. That's what FM, that's what the numbers represent on a radio station for FM. So there's no 1 megahertz radio station, but there is a 96.3, they range from like 90 to 106. It's literally just the frequency in megahertz. If you're in the AM, we had to look this up. The AM channel is all kilohertz. So whatever number it is, that's the frequency in kilohertz. Look at that. And you actually know what it represents. You can tell people around you and no one will care, but you'll find it interesting, hopefully. Welcome to the life of being a STEM person. It's a precious thing when you find someone that cares. All right. How far does a wave travel in a second through free space? Oh my gosh, it's the exact same equation as we started with. How far does it travel? That's just delta x. This is also super easy. 3e8 times 1 second. How far does it travel? 3e8 meters. That is the definition of velocity. So this is a really good problem just to see, do you know what the things mean? The last one is the wavelength. At this one is the math. Actually has some math. Nothing hard. V equals f lambda. Rearrange for lambda. Lambda equals v over f equals 3e8 divided by 1e6. This is something you should be able to do in your head. When you're dividing by scientific, you just subtract them. So 3 divided by 1 is 3. 8 minus 6 is 2. That is a very important and a useful thing for you all to be able to do is take scientific notation and realize when you divide, you subtract the exponents. When you multiply, you add the exponents. Super, super useful skill. Crazy thing here, these are 300 meters long. They're big, long waves. Radio waves are very long waves, but they travel super quick. So just to put this in context for how crazy this is something 300 meters long, and every second, 1 million of them pass through you. It gives you a sense of how fast light is. It's a lot of useful exercises to realize how fast light is. Yeah, 1/3 of a kilometer in size passes through you 1 million times every second. That's light is really fast. But then in the cosmic scale, it's really slow. It's one of those crazy things. And in our little ecosystem of the Earth and things like that, light's really fast. But the second you go beyond that, I think it takes, I always mess this up. Is it 4 or 6 minutes from the sun?
I think it's 8.
8 minutes, yeah, see. It takes 8 minutes for light to reach us from the sun, which might sound fast, but to put that in context, it means if the sun blew up, you wouldn't know for 8 minutes. It's kind of a crazy idea. And then you get light years to other places, and yeah, it's fun. All right, more wave things. Which of the following functions? Now we're going to start to build. Well, we're going to start to build the equation very quickly, or very soon. But which of the following functions describes something that oscillates between 2 values forever? As long as this function is going on, as long as theta increases, it oscillates. Meaning, yeah, you know what the word oscillate means. Cosine theta, sine theta, e to the I theta, or e to the theta. There is multiple right answers. I'm gonna let you pick just one. I'm not gonna tell you how many right answers there are.
Because technically, for
Yeah.
because technically,
Yeah.
Yeah, we learned.
These are all solutions to this equation.
Yes,
The last one is
we were doing theory.
well, the first three satisfy the main equation. So does the fourth one. The fourth one doesn't make physical sense, which is weird.
Yeah.
It's exponential growth or
That's what point is. So like, how does it?
It'll still like spiral, but it like spirals outwards. So it doesn't oscillate between two values. It oscillates.
I feel like I know.
Oh no, it doesn't even oscillate between two
Right,
values.
is it just
But it somehow satisfies the wave equation.
interesting?
Yeah, I'm pretty sure it does. Because if you work the interior cleverly, it's easy to get something. Yeah. It might be missing a negative sign.
Professor,
I don't know.
which function do you like better, cosine or sine?
That's a good question.
That is a good question.
I don't know. I think cosine in my mind has like a negative connotation for some reason.
That's the wrong
But
answer.
cosine's also better because it
When
starts
create
at zero.
series, cosine has a
Cosine is a better answer.
All right, give y'all 5 more seconds. There's not much. I don't want to spend too long on this. 3, 2,
That's one.
1. All right. So hopefully y'all know cosine oscillates. Hopefully you know sine oscillates. You might not know that e to the I theta oscillates. So this is something you may or may not have seen in one of your math classes. Again, if you didn't put that, that's fine. That's why I didn't make this a multiple thing. But I did just want to put this on your radar. If we had covered AC circuits, we would have gotten to talk about phasor diagrams and the real complex plane. It would have been a grand time. But there's something called Euler's equation that says, I think this. I might have mixed up the order.
That's right.
Fun fact, you can write e to the I theta as a combination of a real cosine and an imaginary sine. Why? Look up Euler's formula. Honestly, I don't remember the derivation off the top of my head. I think maybe from Taylor series or something you can get it. I don't know. Doesn't matter. You put any one of these and they're all right. Hey, someone put it. All right, why do I mention this? Well, what does a wave do? It oscillates. So we know that these are going to probably be one of the things. Now, what I'm about to show you is, well, I'll just show it to you. Boom. This is called the wave equation. It's a partial differential equation, which you may or may not have seen. Depends on whether or not you are in the class differential equations. A partial derivative means you just take the derivative with respect to that one variable. So left side has some function, y. It's a function of x and t. The left side, you take the second derivative with respect to x. The right side, you take the derivative with respect to t. And there's a factor of 1 over v squared. Where does this come from? I actually need to brush up on myself where it comes from, but I believe Newton's second law. It's you set up the kinematics kind of equation, and it comes from that, and forces. But it's the wave equation. And in the case of physics, you can actually... Everything I've covered so far is actually something that we're supposed to cover in Physics 1, but we never have the time for. So like this equation emerges from Physics 1. Sine and cosine are viable solutions to this. Fun fact you'll see in when you take differential equations is how do you solve a lot of differential equations? You guess the solution and then see if it works. It's fairly jank. You're going to see that if you're not already in the class, you'll see that that's the thing. They're like, this equation has this solution. Why? Because it works. I don't know. So these are ones that work. But what is nice for us is this equation describes something oscillating, and so do sine and cosine. So it's not a big logical leap to say that, hey, we should pick something that oscillates. Now, here's what we're going to spend the next 5 or 6 slides doing. We need to get theta in terms of x and t. This equation here is an x and t. Theta is not x, is not t. We need to write it as such. So, first step is we're going to get x. That's going to be the, easier one. There's a couple ways. I'm only going to show one of them. The next slide has both. But we're going to use equations you already know. We have already in this class represented distance and theta together. Does anyone remember what the relationship between distance and theta was? We've used it in a bunch of integrals, specifically whenever we had a circle. I heard someone whisper it very gently. We called it S before, arc length. S equals r theta, but we can replace that with an x. That's fine. S is just a distance. X is just a distance. Great. So we're now going to rearrange this. So now theta equals x over r. Just take that and plug it in here. That's step one. Now, we've done something weird here. We put an r. When it comes to waves, there is no radius. Every wave we've looked at, I haven't told you radius because there is no radius. So we can't leave a radius in here. That doesn't really make sense. We're just using it as a tool right now. Now, related to that, currently, whenever you think of the radius, what shape comes to mind? A circle. So we need to go from a circle to that. How are we going to do that? We're going to use another relationship that you all are very familiar with. If I make one full circle, what's the equation for that? What's the distance I've traveled if I made one full circle? 2 pi r. We call that the circumference. Okay? If I travel one full wave, what do we call that distance instead? What's our variable that represents the length of one full wave? Wavelength. So we're going to use this instead of writing c, just to kind of connect from a circle to a, because going around in a circle, as weird as it sounds, it's like a wave. It repeats itself. If you're like, I don't believe you. You've been doing unit circle this entire, how did you do the unit circle? Sines and cosines. You've been doing that. And you were cool with it then. So, algebra. We're going from this fake circle that we kind of made up. R equals lambda over 2 pi, and we just plug that in there. So sine of x over r equals sine of x over lambda over 2 pi. So therefore, sine of 2 pi over lambda times x. Yay! We have written theta in terms of x. A little bit of a funky way, but we utilize circles. We're cool with circles. Waves act like circles. They oscillate. There it is a little nicer. Another way you could do this is you could use ratios. Theta is like 2 pi. You know, there's 2 pi and 1 theta. Lambda is like x. We kind of use that argument, and you could do that with the bottom. That's another way of doing it. It's the same thing. You get the same result. So now we have a wave, but this wave is not moving. This wave is stationary. There is no time component to that. So now we need to do that. That's the next step. We have a function for a wave that varies based on where you're located. Specifically, if I plug in any x value, let's call this x naught, it's going to spit out how tall that wave is at that spot. Okay, that's what a function does. You put in a value, it spits out how tall you are at that spot. Don't lose track of what functions do. All right, the time component. Remember, these waves move. So this graph shows two waves. At time equals 0, that is our, let's call it the blue wave. So that's going to be, unfortunately, it's the dotted one. So this, I'm going to recolor them just to make it a little easier to see which one's which. They are labeled, but, so the blue wave is at time equals 0. And remember, I told you these waves move. So this wave at some later time is the orange wave. It has shifted itself. It's moved. It's traveled. It's physically moved in space. So we have two graphs for two functions of time. And yeah, just to draw this, how much we moved is this big red arrow. We moved to the right. This wave moved to the right. I know it looks like it moved to the left, but moved to the right. That's going to be important for us sometime later. All right. Okay, so here's the same picture. At t equals 0 seconds, sine of 2 pi over lambda 2, that's my x coordinate. So at x equals 2, my y value is 6. You can see that in the graph. That's where the dotted thing is. My question to you is at t equals 3 seconds on my new graph, what is my x value that gives you the same result, gives you the same height? This is not mathematically determined. It's done by reading the graph. At what x on the different graph, not the dotted one, but the solid one, what value of x gives the same result? Here you're looking at the solid line graph. T equals 0 with the dotted one. We're done with that. Look at the solid one, and at what x value do I get the same y value? At x equals 8.
I didn't realize.
It would be, but yeah. There are always infinitely many after this, but
Of course, you can minus go up or down. Well, what was my original x value? Oh, yeah. What was my original x value?
Say it again. So it's saying at t equals 0, which is the dotted wave. Sine of t at 2 centimeters is the height of 6 centimeters. On the dotted one, when we get the same way.
Okay, so you're just kind of
Yeah.
I hit a point of no return before either I. It's 2 a.m. No, that's
Yeah. They sound like thunder. There's a law against planes going faster than the speed of sound over residential areas over land because the sonic booms are so loud, miles away, and they can break glass. And things like that. Yeah, they're really strong.
From like rockets from NASA.
There's no law against that one. I mean, they don't have a choice.
Isn't it by the time they break the speed of sound is so far up that they don't cause like damage? Like they're not breaking glass.
Oh, it depends how close they are. The wave will, the farther away it gets, the intensity gets weak. But if they get close up to the ground, it can break glass. It can actually kill people if it's like really close to the ground. Yeah, there's so they sometimes have air shows, and they are allowed to do it during air shows and things like that. Or generally any testing. Generally a rule. That's one of the reasons why there's no supersonic flights in general. Is there's a lot of regulations against it. If they did supersonic flights, they would basically exclusively have to be overseas. There's no.
There's also a lot more laws that test that happen.
All right, 5 seconds, because either you know what or you don't at this point. All right, 3, 2, 1. So we're just looking at the solid line, and when does the solid line also equal 6? That happens at this point right here. This is when it also equals 6. When does that occur? At x equals 8. All right. Here's what I'm now going to attempt to justify to you all. Using this graph, we can understand how the time's going to come in using just basic physics 1. What was my original x value? 2. What was my final x value? 8. So did it go up or down? Went up. So if we kind of look at this, we have the sine of 2 pi over lambda 2, and the other one's 8. To return back to my original value, to go from the 8 to 2, I need to go down. Like if I want to go backwards in time, kind of, sort of, I need to go down. So what does that mean? I need to go so I went from 2 to 8. This distance here, that's delta x. That's how far the wave traveled. What was the equation for delta x that we should really remember from physics 1? It's vt. So At time equals 0, this term didn't matter. At time equals 3, it did matter. So if we kind of think about this, if I want to go from 8 back to 2, if I want to go from my new x back to my old kind of value, should I subtract or add? If I want to go from 8 to 2, subtract. At time equals 3, if I want to go back to my original value of 6, if I want to have one equation that represents all this, I need to reduce the value back down again. How do I reduce the value? I don't add VT. I subtract VT. That's kind of the major idea I'm trying to convey. So, if we kind of write this here, we have sine of 2 pi over lambda. And we had that x value. If I want to return back to the original 2, the new one, so I'll show the math one later. It's going to be easier, which is what I have written down there. So this is the idea. This wave travels. It travels, in this case, to the right. I need to shift it back to the left so that I get the same value at some x. How do I shift things left? I subtract it. So that's one way of thinking about this, is the idea that we're shifting this wave such that this value, let's call this, 2 and this 4. How do I make 4 go back to 2? I need to, let's make it a different number. How do I make the 6 go back to 2 so that the function returns the same value? You have to subtract something. What am I going to subtract? This distance. What is that distance? Delta x, which is VT. So that's shown here. So there's my original, sine of 2 pi lambda x naught, and x equals x naught plus VT. If these two things are equal to each other, then I have to subtract to make that x into that, to make that x naught back into that x, I have to subtract. So that's that. It's a kind of a funky thing to try to explain. But the VT is just because that's the distance my wave traveled. The reason we're subtracting is we're shifting the wave back to the left. That's the two main pieces you all need to know. Also, what's important here, which way did this wave move in this picture? If it moved to the right, which way was the velocity, positive or negative? Not a trick question. If I move to the right, positive or negative? So something that we're going to see in just a second, this negative sign means a positive velocity. Why? Because if it moves to the right, I need to shift it to the left. That's kind of what we're doing mathematically here by including this term. Shifting it back to the right so that we return. We're basically trying to take all our function as time goes on. We're trying to shift them back to the origin. That's what this minus VT term is doing. So great, there's a wave equation. It's all those pieces together. You got your 2 pi over lambda with the x. Then we have this minus plus VT to help you remember that the velocity is opposite. So if it's negative, the velocity is positive. If it's positive, the velocity is negative. And there's one last thing in here that I'm not going to actually test you on, but I put it here just for completeness. We have something called the phase angle, and this is how shifted the wave is. Because not all waves at time equals 0. In the case of a sine function, at time equals 0, you have the maximum. What if that's not true? What if at time equals 0, it doesn't start at the maximum? What if instead my wave starts like this, not maximum, something in between? This phase shift lets us account for that. So I'm not going to test you on that, but it is a very normal thing for these waves to be shifted. You don't always get waves that perfectly start at the origin or perfectly start at the maximum. Sometimes, it's somewhere in between. And yeah, this last point, very important. If you're subtracting, the wave is actually going to the right. If you're adding, the wave is going to the left. The one on the left is what's on the formula sheet. The one on the right is another very common way that this is written. We take that 2 pi over lambda and we bring it inside the equation. So we do this, we do sine of 2 pi over lambda times x minus plus 2 pi over lambda times v times t plus phi. So we transfer it on in. We just call that 2 pi over lambda the wave number. Why do we call it that? It's to make it, if this was a spring, it would be k, which would be the spring constant. So this k is kind of analogous to a spring constant in some ways. but it's just maybe a little bit cleaner way of writing it. This omega equaling 2 pi v over lambda, I'm going to prove that to you very quickly. Again, using our circle technique. If you all remember, we took lambda and we said lambda was like the circumference of a circle. How do you find the circumference of a circle? 2 pi r. The 2 pi's cancel. So you get that omega equals v over r. And this is literally the definition of omega. This is how you go from angular velocity to regular velocity. Just like how do you go from distance, angle to distance? You just multiply by r. You do the same thing with angular velocity. Great, so there's the derivation there. That's the proof for you all that is true statement. And now, I've said this many times in this class that math is a language. This is a sentence. We need to be able to read this sentence. So now I'm just going to give you all some equation. The next problem is going to be, hey, here's an equation. Find this, find this, find this, find this. Find the velocity, find the amplitude, find things. So here's a wave equation. What's causing this wave? Who knows? We don't care at this point. We're just getting used to reading the sentences. Then we'll start to make sentences that apply to real-world scenarios. So here's a wave function. 3.0 sine of 0.4x plus 2t plus pi over 10. And it's in centimeters. Be careful of that. The output will be in centimeters. The question is, what is the amplitude of this wave? What is the period of this wave? What is the wavelength of this wave? What is the wave speed? That's another phrase for velocity. Absolute value of it, but actually, I'm going to change this word speed to velocity because I care about the sign. In the initial phase shift. How do you do this? Take the equation I just gave you, compare it to this one, and build some relationships. Try it out. And you know what? I'll even write it here for y'all. So that's our form, and you need to take this one, which has numbers, and match it to that one. That's the general form. All right, great. I did the same thing. got 5. I'm not ready for that, so I don't trust myself.
You probably did it nicer, but
Oh no, I looked it up.
I pulled up. You just pulled up on 4, so you get 2.
She also got 5.
I'm gonna write it down. I don't trust myself. Alright. So the key here is, if you're not sure how to get something, find something else instead. Might be one of those multi-step things. That's why I put. Notice I didn't solve for period yet.
Velocity is just mean, right?
Oh yeah, no, I butchered that. That's bad on me.
That's the same as 5, right?
Yes.
And then it's 5.
There we go, I got 5. There you go, centimeters per second.
2 pi divided by 2. So just pi. The term of this.
All right, and the other ones I won't put because they're too obvious.
Also, apparently, the other form of it, the omega, it's just 2 pi divided by 2.
Two equations to each other and building it out.
That makes sense.
Where's the 2?
Oh, it's
Couldn't remember that.
something I recommend: take that 2 pi over lambda and factor it into the parentheses. Make them look like each other. That's gonna help you build some relationships. That's fine. Yeah. At the end of the day, they mean the exact same thing.
Yeah.
So if there's a free response, they do the same thing. If it was a multiple choice, whatever the answers are in,
Yeah.
But, yeah, 15.7 centimeters is the exact same thing as 0.157 cubes.
What about radians? Something instead of like,
So
if you have like radians per second, as long as you multiply
depends what they want.
Okay.
If they want angular frequency, then it's radians per second. If they want regular frequency, then you gotta convert. You gotta get rid of that radians.
Because the radians is the same no matter the radius.
Yeah. Radians is an angle. It's your kind of where you're at in your process, in your cycle, as it were. It's your, and the idea is once you've gone 2 pi radians, you've done a full cycle.
Yeah.
No matter what, no matter how big your circle is, no matter how big your wave is, no matter how big whatever the oscillation might be, when your theta iterates over 2 pi, you've got a full cycle.
But if you're going into something like trying to go to velocity, like you need to just say the whole what's the equation. You're going for meters per second.
Yes, if you want meters per second. Yes. Yeah. I love the centimeters. I think with centimeters and
Yeah, it's just easier.
yeah, it was just easier. But base units is always it's a good practice to get in, just because all equations are calibrated for that. And in this case, I knew I could keep the centimeters because I knew they'd cancel out when I did period. But you have to know when they're going to do that, and that takes doing function problems. All right, how y'all doing? Nice. Great. I was like, that's honestly, gosh, probably a third of the problems I put together are just playing around with this equation. And you might say, hey, given this, build the equation. Or in this case, given the equation, find this. Yeah, it's capital T.
Yes. I go there. I know very I get up for this first year.
Yes.
They give like huge portions of it.
Now, if you know that this is one of One over this.
Oh,
Yeah, or the overlanded one, but yeah. Very nice, very nice.
For my 21st
All right, so there's me factoring it in, and just to kind of help us move things along, let's pick the things that is the easiest to solve for first. The easiest one to solve for first is lambda. Why is that easy to solve for? Because that just equal this and this equal each other. You can just look at the two and see that they're the same spot. So therefore 2 pi over lambda. So I'm not actually going to solve it in the order that the problem told us to, because that's actually, at least for me, it wasn't the intuitive first step. So 2 pi over lambda, 0.4. Therefore, lambda equals 2 pi over 0.4, and that equals 15.7. Now, it's in centimeters because that's what this function's in. This function's in centimeters, so we also need to be in centimeters. I should have said here x was measured in centimeters as well. Technically, the way I wrote that centimeters says that y is just a function of it, but we'll assume y and x are in the same units. That would have been better if I had done that. All right, great. Now that you have that now unlocks the capability of doing this one. Now that I know lambda, 2 pi over lambda times v equals 2. Why? Because they match. Matchy, matchy. So 2 pi over lambda times v equals 2. Now, there is something that you can do here to make your life a little bit easier if you wanted to. 2 pi over lambda equals 0.4. It just makes the math maybe a little bit easier. That's the definition of 2 pi over lambda. We defined it already in an equation. So it makes our life just a little bit easier. This is much easier. I could do this in my head. Calculators are always safe, but this is something you can do. It's, again, we'll assume centimeters. Great. So now you got velocity. Oh, something I didn't put here, though, that's very, 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 very important. Which way is this wave moving, right or left? Left. Why is this wave moving to the left? Because, remember, they're the inverse. That's why we have this minus plus here. It's the opposite. Whatever it says, it's doing the opposite. In this case, it says it's plus VT. So this is, in fact, a negative. Or if you wanted to maybe write that, maybe make that a bit more clear, negative 2 pi over lambda v equals 2. If we want to write that mathematically accurate. All right, great. So that's negative, negative, great. The period, there's a couple ways you all can go about this. Funny enough, the way I kind of did is I re-derived it. So what is period? It's the time it takes for one wave to pass. So there's a couple ways that we can do this. I'll mention both ways. One, the first way we're going to do it is we're going to derive the expression using our physics 1 knowledge. What is period? Period is the time it takes to travel. So, delta x equals vt. Period is the time it takes to make one full wavelength. Why? Because that's the definition. Period is the time it takes for the wave to travel one full wavelength. So delta x becomes lambda, v is v, t becomes capital T. T is the period. So t equals lambda over v. And great, you can plug in the numbers. That's one way to derive this expression. The other way is I taught you all that v equals f times lambda, and t equals 1 over f. If you put those two pieces of information together, you can also determine the period. It's the same expression. So pick your favorite. It comes out to exactly pi. Great. Seconds. I didn't put the amplitude on here because it was too obvious. The amplitude is 3. Great. What's the phase shift? Also too obvious. Pi over 10. So what this means is this is a sine function that doesn't start at y equals 1. If you put x equals 0 and t equals 0, the value of this is not a. It's shifted. In the beginning, if I like drew this function, this is some function shifted. And I gotta be careful here. Shifted plus phi. I'm gonna say it's shifted to the left. So this is a sine function that is normally a sine function does this. It starts at 1 and it goes down. Plus phi should be shifted to the right.
Sine starts at 0.
Yeah. Sine starts at 0. Well, I'm trash at this. All right, sine starts at 0. We all know that because we don't make mistakes like me, right? So it's shifted to the right. Some amount, pi over 10, which is not pi over 2, which is right true. But that's what the phase shift is for. Great, so fun. All right, take a breather. We're not going to go the full time today, but there's a bit more I want to cover. So take a break, though. Waves. My head's not hurting too much, so hopefully your head's doing okay. I don't know. But we'll do a little bit more. Not a ton. Series of parallels. Are they doing it?
Pretty.
Generously 7 out of 12. And they do C squared of R. But
Wait,
they
is that
combine
12?
that. No,
Okay.
the lecture one is. Because I bumped theirs down to only 3 questions out of 4, and 3 didn't divide nicely.
That makes sense, yeah.
40, so I made them out of 36 points and made it out of 12. Yeah, this one they do pretty darn good.
Yeah.
So it's pretty easy. They just surprise you. Not half of them, that's just useful. Which is a little.
Okay. I saw it more in
Or
the,
no, I just have to take
your
the
other
bus so
version.
that way we make sure that we
Yeah,
get
because it had the easel.
They messed up that.
Yeah.
The one that. Oh, this.
Yeah.
Some of them. So one of the ones that I was going to was this one.
Yeah.
Not very good.
Yeah. I saw people here with like the DDT, they integrated, which like does end up giving us a sign, but like.
But it puts the omega in the wrong spot.
Yeah, exactly. So, yeah. It evens itself out.
So this one probably people get a lot of easy points. This one, I've had few people get the exact right answer.
Yeah.
They almost, a lot of them forget this. I had some people find the directions in odd ways. And it's
Yeah,
not like
I had more direction issues on this one. Yeah, that's what I'm noticing. People get the direction right on this one, but sometimes they mess up.
I haven't graded this is my
I'm
electric
on
class.
my second stack.
Oh,
I want to be done before the weekend.
yeah. That's good though. That means I'll be able to put the grade. My goal is also be done with it all.
I have the spreadsheet ready.
I will tomorrow. Yeah, because I also plan on being done tomorrow. Yeah, I'll make sure to get that done. And then, yeah.
This one is hard to do a partial credit in my opinion.
It is, and that's why I've been teaching.
Okay, yeah.
They know to add the resistance. I've been giving it so as a simple that comes out to about 16.
Yeah, okay.
That's kind of if I see that they did the power and messed up some of that. It's probably more generous than it should be, but so 6 out of 10 is probably what I'll give to those. If I see they did not know how to, like they didn't realize what was
Like here, it's really just like that you should put them in the denominator here.
Oh, that's a tiny mistake. Okay.
Yeah, yeah. So this one, like, yeah.
This one they didn't know which ones to combine. Okay, so I give more. Mine were like they just combined the wrong ones.
Yeah,
That's where I was getting
I've seen
stuck.
some of those too, but okay. So this is like, would this be like an 8 or a 7 in your opinion? It'll give me an idea of how big.
See if they actually combine. If it's not clear, then I'm gonna get points. So here it's really not clear what they combined. They put the word series, parallel,
So this one might be 6.
Okay.
Like which 3 resistors you're working by? I have no. I think it is these ones. But then they have an extra 3.
That comes in, yeah. So it's like, are you saying these 2 of them? Yeah.
So that's.
That makes me feel better about how I'm doing so far.
Okay, you've been doing similarly?
Yeah.
I feel like that's the skill. Can you identify certain? Yeah, I will start working on the final next week. I'll be gone on Friday. No.
I was surprised by people mixing a manual frequency and frequency.
Oh. You're not open.
So like a fair amount, like everything is correctly just plugged in like 2 times.
Well, to be honest, my lecture class, most of them didn't choose that much.
Oh, okay.
Because if you know what you're doing, it's easy.
Yeah.
If you don't know, if you don't know that you have to set up that, like,
Yeah.
that is very much a, you don't know how to do it. There's not much.
Yeah.
Whereas like the resistors one, you're kind of like,
Right. You can attempt it. I do wonder how I would have done this. I feel like it's nicer than the one I took.
I think so too.
But it was probably just experience.
All right, y'all. Here's a problem. Here's 2 more waves. My question is how their velocities compare. So I got 2 waves. One's 0.4 sine 2 pi over 2x plus 2 pi over 2t. Next one is 0.2 sine 2 pi over 2x minus 2 pi over 4t. How their velocities compare.
Yeah, I did think through.
Yeah, it's just so the way I was taught was like you don't like pull out the ends, you don't like bring in the 2 pi over lambda. Yeah. So I just estimated, okay, let's pull out the 2 pi over 2.
I just did a ratio.
That, yeah.
You just divide the whole function by each other. Yeah. Or just the
inside, yeah.
the T code. Yep. So no, it's one of those things that people don't know they can do.
Yeah, it's a hack.
Yeah. So it is a cool one.
Oh, it's great. It takes a while to understand why you can do it. It's a really hard thing to teach.
Yeah.
I feel like people benefited from the fact that I didn't
You play C and Q variety of penmanship.
That's kind of nice. Like, that's incredible. Right?
Yeah.
And then where have
Yes.
No, I mean, figure it out. You don't have to pick my answer.
Oh yeah.
That's my.
Yeah, that's my answer.
Reading to that's up here, like old Catholic. Then I get out.
How are y'all doing?
Hello.
I should have got 85. Great. It worked. All right, looking good. I'll give y'all about 10 more seconds, but I'm pleased with what I'm seeing and hearing. Y'all are understanding the wave equation? All right, in 5, 4, 3, 2, 1. Boop. All right. So the way again, we want to always have this wave equation somewhere in mind. A times sine of 2 pi over lambda times x minus plus vt, and there's no phase angle here. So we factored in the 2 pi over lambda. So what that means is that this is the 2 pi over lambda, whereas this term is 2 pi over lambda times v, but because it's the same value, v1 equals 1. Positive or negative, though? Which way is wave 1 moving? Left or right? Left. Wave 2, this. So thankfully, I made your life a little easier. I made the lambda exactly the same. So this is my lambda for this one. This is 2 pi over lambda times v. With math, we find that v is 1/2. That's how we get it from a 2 on the bottom to a 4. So we get v2 is positive 1/2 meters per second. What's the relationship between these? v1 is twice of v2. So that's what we find. And that's pretty much what I see everyone got. Now, there is a handy little expression here. So I've told you all this. I mentioned it before, but just to kind of write it out again. Sometimes you'll see these wave equations written like this. A times sine of kx minus omega t. So this is another way of writing it. it turns out that the velocity, and I always have to check myself on this, it's either k over w or w over k. So I'm just going to quickly do the math here and see which one works out right. If we do 2 pi, I forget this one off the top of my head. I think it's omega over k. Think it is also, yes, I think it is also omega over k. So this is just a handy little thing. It's not on your formula sheet, but it is, if it's written in this form, you can just take the omega divided by k. And why can you do that? It's because k equals 2 pi over lambda, and omega equals 2 pi over lambda times v. So, I mean, you can just see it. If I divide those two, you just get v. So that's why. Yep. Handy little relationship. All right. So this is, I don't know exactly how much farther I want to get to, but I do want to talk a little bit about this next part. These are just been general waves. I didn't say what made these waves. I didn't say what they were doing. Like, this was just math. Up to this point, this is just math. Hey, these are waves that are moving. Now we finally get to connect it to light. We had to understand, we had to be able to speak the language before we can apply it to the real world. So, these expressions are derived expressions. They're going to look very similar to the wave equation we had before. You're like, what wave equation are you talking about? Way back, not too long ago, I gave you all this expression. I said, hey, if you take a function, the second derivative with respect to x equals 1 over v squared, the second derivative with respect to t. It turns out that if we do Maxwell's equations, which I haven't taught you Maxwell's equations, well, I haven't. Maxwell's equations are the 4 equations that explain all of electricity and magnetism. And I have technically taught you most of them. One of them is Gauss's law. One of them is Gauss's law for magnetism. I didn't teach you that one. I did teach you Faraday's law. And I did teach you Ampere's law, but there's an extra contribution that Maxwell added. If you're a physics major, you're going to see them in all their glory later on. If you're an electrical engineer, you'll see them later in all their glory. The rest of you, this is probably the most you'll see. But if we do some clever stuff with Maxwell's equations, we get these expressions. The derivation for this is not a simple one, so I'm not going to do it. It's a lot. But you get this. The second derivative of the e with respect to x equals the second derivative of the e with respect to time. Wow, it's just like the other one. And then we also get a relationship between b and e. Specifically, that the z component of b with respect to time equals the e component with respect to x. We'll use that in the future. This first one on the left is the main one. It looks a lot like the wave equation. I really hope, look, here's the wave equation that we just wrote down before. Just to make sure you all can see that they look very similar. This is the one that came before. Partial, not regular. These partial symbols are always a fun time. They're very similar. What does that mean? Our solutions that we've been using apply to this. What does that mean? Light's a wave. Yay. That's the big kind of takeaway here. We generate an equation whose solution is of a wave. This is the theoretical proof that light is a wave. And then there's lots of experimental proof as well. It's pretty well founded at this point. All right, now we're going to do something cool with this, though. Here's the two. The one general one and the one that has to do with electric fields and magnetic fields, or in this case, electric fields. Both of these are true, and they both have the same solution. With that in mind, what is the value of V for an electromagnetic wave? Just look at these two equations and basically pretend they're the same thing. And I want to see if y'all can solve for V. And fun fact, you can check your work. We know the value of V for an electromagnetic wave, but we'll calculate it in a second to prove it. But they just come from comparing these two expressions, and if they're both true, they both have the same form, then we can do that. And just to make sure, you all don't need to know anything about partial differential equations to solve this. It's just comparing the two, and where does V show up? Where does other things show up? Make them equal to each other. Algebra.
Am I doing it? I haven't even looked at any of these. Yeah, agreed.
And whatever you all answer, what I really want you all to do, whatever you decide the answer is, I want you to plug in your calculator and see what it spits out. You might not, look, I'll remind you all the values. These are numbers. Epsilon naught is 8.854 times 10 to the minus 12. Whatever answer you decide, I want you to actually plug those values in and see what it spits out. It's cool. I haven't actually done this myself. I just assume it works. Theory 7, right?
Yeah.
Great.
Or I forgot my assignment.
Yeah, great.
That's
Mine
right.
works. Plug it in. You'll get a really cool answer, hopefully. It should be a really cool answer. I don't know. I know it comes out right. Alright, what y'all decide? Whatever you it's cool. You get a really cool number that you'll hopefully recognize. You're just comparing these equations, you get a really cool result. Alright, what'd y'all get?
Tell me that
That number looks what is it? What is it? You solve for B. What is it's cool. Anything? Now, granted, that's one not too but using you get a really cool result. You don't actually have to measure the speed of light. You can measure epsilon naught mu naught. Yeah. Speed of light's pretty hard to measure. It's pretty cool. Around that. Great. All right, give y'all about 10 more seconds. All right, in 5, 4, 3, 2, 1. All right, so you get 1 over v squared equals epsilon naught mu naught. You just compare them, and those are in the same spot, so great. Therefore, v equals the square root of epsilon naught mu naught. Great, that's my answer. I really hope you all did try plugging this in, because when you plug it in, you get a really cool number. You get 2.99796. There's a reason we often round it. E to the 8 meters per second. If we round that number, it might look a little bit more familiar. We solve for V. V for an electromagnetic wave, which is light. Oh, it's the speed of light. So what's really, really, really cool about this is you can determine the speed of light. Now, epsilon naught and mu naught are measured experimentally. Those do come from experiments. But specifically epsilon naught is. But from those, you don't actually have to look, measuring how fast light travels is not an easy thing to do. It's really fast. You know, you can't just get a meter stick and a stopwatch and turn on a light bulb and measure it. But epsilon naught and mu naught actually aren't too hard to measure. You know, you can do capacitors and things like that to measure them. And from that, you can get the speed of light kind of through other experiments and things like that. This is a pretty common thing that values we want to measure, we can measure them indirectly. And it's a cool thing. This is the speed of light. It comes from theory. Now the theory, again, based on experiments, it all intersects. So great. There's the speed of light. It's how fast light travels in a vacuum. Now, technically it is how fast light travels through everything. It's how fast light travels. We are going to, at some point later on this PowerPoint, I'm going to tell you light travels faster or slower in materials, even though it actually doesn't. I'm going to tell you that. We'll see it when we see it. This is the fastest anything can travel. Nothing can travel faster than this. And when I say nothing, specifically the phrase we use in physics is information. Information, this is the fastest I can transmit information from one location to another. It is impossible to transmit information faster than this. There is no way that we currently know of to do so. This means that if you want to communicate with a rover on Mars, this is the fastest your signal can travel. If you want to look at a star, if you want to determine what's going to happen on some other planet, the light that you are seeing from said planet had to travel this speed to get to you. So, for example, if something's 6 light years away, that means you are viewing what it looked like 6 years ago. Because that's the fastest information could get to you over a very long distance. So this has lots of I'm going to use the word profound consequences. Nothing can travel faster than this and when I say as far as we currently understand that, you should pretty much tack that on to anything I ever teach you. Remember that what I'm teaching you is our current best understanding. Is it right? It's got pretty good evidence, but we've been wrong in the past and we'll be wrong again. Never assume. A very important thing in science is to be healthy skepticism. Don't doubt everything, but do have ask questions. If someone tells you something that's maybe unsure, look things up. It's not an insult. Some people do take it insulting. I tend to do this a good amount. Someone will tell me something, I don't believe it, I'll look it up. They tend to not like that. But sometimes they're wrong. And you just got to present it in a nice way when you look up things. It is a part of being a scientist is a healthy skepticism. Don't doubt everything, but do recognize that everything we understand is just our best understanding. All right. This next slide looked like a lot of things, but all I did was replace V with C. This looks like a lot, but literally all I did was I took our original wave equation and replaced, instead of an amplitude, it is an amplitude. It's the amplitude of the electric field. Instead of velocity, it's C. It's the same equation. Let me write that equation up here so y'all can be here. You know what? I'm going to write it out more slowly because anytime a bunch of equations like that show up, people's brains get destroyed. I know how this goes. So let's just write this out, a little bit at a time. So this is the equation that we used before. Hopefully we were cool with this. Maybe not, but whatever. That's it. Hopefully that's not intimidating. Now, instead of a y, we're going to be measuring the electric field. This original equation comes from the electric field. Now, the electric field is a vector. That matters. But for now, whatever. So the electric field is a function of x, and this is the electric field in the y direction. So that's something important here. I mean, that's, y and y. This is a vector, so this is the value of the electric field in the y direction across x, and this equals, instead of my amplitude, I'm going to put E naught. That's my amplitude of that's the maximum of the field. I still have 2 pi over lambda. I still have x. What's the value of the speed? What's the velocity of the speed of light? It's a c. Great. That's the equation that shows up on the next slide. Okay? So just so you're not super into it's the same thing. It's the same equation we've been working on. We just replaced A with E. We replaced B with C. That's it. That's all I did. And you can replace 2 pi over lambda with K. That's the wave number. That's not it. We showed that before. Omega, again, had that before. Now, something that is a little bit of note here. This electric field oscillates in the y direction. So that's, let's just say the y direction, let's say that's up, down. The magnetic field oscillates in the z direction. Which way is the z direction? It's 90 degrees to that. So one oscillates up, down, one oscillates left, right, and then the wave itself is traveling in the x direction. So the wave is traveling left, right, and the electric field oscillates one way, and the magnetic field oscillates perpendicular to it. That's the idea here. There's some nice, better pictures of it somewhere else. Actually, you know what? Let's just go back to the beginning. That's where the nicest picture I have. So the first picture I showed you all. This field travels in the X. The E goes up, down. That's the Y direction. So this is the Y. The is this way, and the X is this way. We need all three dimensions because it's wiggle-waggling its way kind of along. So it's an electromagnetic field. It has both components. And that's, I don't know, that's just kind of a cool thing. They're tied together. They're tied. You do not have any light that's just an electric field. Why? It turns out that a changing field results in a changing magnetic field. A changing electric field makes a changing magnetic field. They're coupled together. You can't have one without the other. It's something I haven't done a great job of explaining. All right. Last thing. So I'm not going to get too much. So we showed that. I'll do that one next time. Kind of the last thing I just want to show you all, just to leave you with something practical. How do you make these waves? So we said they're waves. One oscillates up, down. One oscillates left, right. So, just to think about this a little bit more. How do you all make, if I had a string, how do I make it make a wave? I wiggle it, right? You wiggle the wave up, you wiggle the string up, down. How do y'all, I'm making sound. Sound is a wave. How does my body make sound? I vibrate something. So long story short, every single wave is made by wiggling something. Whatever it might be. You want a physical wave? Wiggle something physical. You want a sound wave? Make the air molecules vibrate. You want an electromagnetic wave? My question to you is, what makes electric fields? What's the thing we learned in our third week of class? Charges, electrons. So what are we going to wiggle? Charges. If we wiggle a charge, we make an electric field and a magnetic field. Now, how do we make it? Something we've kind of been doing this entire class is we have said, hey, find the electric field at this point. We have not had any fields that varied with time. We never moved a charge and said, what happens to the field here? So I'm going to show you a little animation for how to make this. There's a couple of them, but I'm going to use this radio tower one. They haven't updated it, but I think it's one of the best ones I've kind of found for this. So all antennas, every single thing that is generating these waves is just a wire that you make charge wiggle up and down in. That's what an antenna is. It's literally a wire that you make charge wiggle. So, great. And as it wiggles, it makes a field. So I'm going to pause this for a second. So this is my wave. Now notice that this wave, where do I pause it? There we go. What is the direction of the electric field away from a positive charge? Does it point towards it or away from it? Away from it. Oh, look, a field that points away from it. But wait, over here, why isn't the field pointed away from it? The field should point away from it everywhere. Information takes time to travel. Just because this charge moved down, way over here, it doesn't know that yet. Information does not travel instantaneously. If I move a charge, the field 1,000,000 miles away has not updated yet. How quickly does it update? At the speed of light. So what we're actually seeing when we see this wave traveling is we're seeing the electric field updating in physical space over time. And this is obviously much slower than light actually travels. But this is the idea. As you wiggle this charge, it makes the field change. But that field changing propagates through space because that space doesn't know that the field changed until some time later. Until some later point in time. And to give you all an exaggeration of this, it's got a nice little, I can show you the entire field. So here you all can see the field kind of wiggles up and down. And, for some reason I thought it updated in more places. Sad. So you can see here the field oscillates. It didn't show in other places. I thought it did. I thought I saw it somewhere. Oh, well. Oh, there we go. This is what the electric field actually looks like in all space. So this wave radiates outwardly everywhere. This is pretty useful for us because you don't know where your antenna is going to be. But this field takes time to update. This up arrow is traveling along, not because it's physically moving, but because this space finally realizes, oh crap, this charge moved. And it took time for that to travel, and you get this kind of macroscopic effect. And then what happens here, how does another antenna work? Oh, that antenna's got electrons in it. What happens when that field reaches that electron? It causes it to wiggle. When the field is up, the charge goes up. When the field is down, the charge goes down. That's how antennas work. They're literally just a hunk of metal that when these fields hit it, it wiggles the charges in them. And you get the signal, the original signal. You notice they're just delayed by each other because it takes time. Information does not travel instantly. It takes time. This one's more complicated, but it is still pretty cool. So there's a simulation here. This is a half antenna. And again, you can see this effect. I think I can zoom in somewhat. You can see here the current. In this case, the current goes up, the current goes down. What does that mean? Charges go up, charges go down. And this causes the field to wiggle, and you get these electric field and magnetic fields. And, it's great. If you want to make it just the electric field, you can just show. That one's a little messy. There's the electric field lines. I accidentally added an element that I didn't mean to. Oh, well, broke everything. But this is how all wireless communication works. All antennas are just loops of wire. Oh, yeah, there was one more I wanted to show you real quick. Sorry. And then I'll spare you. This is a half antenna, but they also have a current loop. And what is a current loop but a thing that the current wiggles around, and ta-da, you make a wave that goes radially outwards just by wiggling it. And you can slow it down because this is pretty fast. As the current wiggles one way, it makes the field one way. As it wiggles the other way, and that information, when the arrows are down, it takes time for that arrow down to information travel. It's cool. I don't know. I think it's cool. This is how all antennas work. All wireless transmission works. It's just current wiggling up and down. And the faster you wiggle it, the higher frequency of the wave. The slower you wiggle it, the less frequency of your wave. They're directly coupled. Great. All right, that's good enough for now. Play around with these things, y'all. It's cool.